ESF is the oldest, largest, and most distinguished institution in the United States that is focused on the study of natural resources and the environment. Hello and welcome to this edition of Improve Your World with SUNY-ESF. I'm Dave White. This edition of the program will be very constructive, and I mean that in a literal sense. We're going to talk about construction of the college's very first student residence hall. We'll also go through the construction of a new parking lot. In both cases, these are construction projects designed to test and demonstrate a variety of green construction practices. We begin with a quick summary of the residence hall construction process. Next up, we hear from some of the people involved in the construction process of Centennial Hall, and they explain what makes it so unique.
My favorite thing about being able to perform this project for ESF is that it's right in our backyard, and it's an institution that has a lot of lineage with Hubert Brewer. My father, Jim Brewer, was a graduate. My grandfather, Vic Brewer, was a graduate. So the affiliation runs deep. I think most importantly, we employed a very unique approach here with the modular approach that allowed us really in 12 months to turn what was formerly 18 separate homes on Oakland into now 450 beds in this new 135,000 square foot dormitory.
All those buildings were shedding all of their water onto driveways and off their roofs and into gutters, and everything was coming out into the street, working its way into the city sanitary and going off site. And it was, the whole place was just overgrown with weeds, just invasive species weeds. Now we have a site that can handle all of the stormwater from, I believe it's up to a 100-year storm, can handle all of the stormwater, and now the entire site is planted with local and adapted species. We've incorporated a lot of green aspects into the project, a lot of different construction techniques, a clean building environment, which leads its way into a clean living, working environment. All the materials you see around you are all low VOC, low emitting materials, from the flooring to the adhesives to the paints, even the vinyl products that were incorporated into it.
The timber tower itself is approximately 12 by 12, 56 feet tall at its highest point. It's made of 12 by 12 glue laminated Douglas fir posts or columns, and then all of the horizontal connectors are solid sawn, kiln dried, radio frequency kiln dried Douglas fir beams. The roof is made of 10 1/4 inch SIPS panels. It's a EPS foam material, and those will be installed shortly after the tower is erected. After the tower, there's a western red cedar trellis that is fresh sawn, so it's green material, about 15% moisture content, and when it's installed. And then another specific would be all of the roof overhangs and the alcoves of the building are fresh sawn Douglas fir, and those will be exposed. So that'll be a nice incorporation of timber throughout. We're actually in the process right now of doing life cycle analysis on timber frames versus conventional frame structures, and thus far we found, although timber frames are more imposing, look much larger, the board footage of material used, for instance, so the volume of wood is lower in a timber frame, efficiently designed timber frame. So it's really a greener way of building, in my opinion, although it looks, the volume looks very large. Yeah, the pegs are ash, the frame is Douglas fir, and with the exception of those couple bolts, it's all wood.
The building has a very sophisticated energy use system. We use water source heat pumps to heat and cool the entire building. They natural gas-fired boiler plant that covers the heating, and a gravity-fed evaporative cooler, which covers the cooling. We're basically saving somewhere between 21 and 23% on energy of a normal building without using kind of a traditional technology. So overall, the building is very tight. It captures its heat and coolness and holds it very well. It's generated in a very efficient manner, and a lot of times what you run into in a building like this where it's very tight, it becomes stuffy, and you have carbon dioxide issues where people are constantly breathing the same air, just recirculated. On the roof of the building, we have energy recovery units that are introducing fresh air at a constant rate, as long as there's inhabitants of the building. And what that happens is the stale air coming out of the building goes through a sort of like a membrane almost, with the fresh air coming into the building, and the warm air coming out, for example, in the wintertime, will heat the cool air coming in, and so you kind of gain that energy back when you're exhausting the cool air. So in addition to being very tight and very energy efficient, it's also loaded with fresh air.
We had our concerns about how these modules would fit together, both in terms of just the levelness of the floors, and would you see a lot of cracking? Would there be problems with some of the mechanical connections? In general, there were certainly a few hiccups and hurdles, but it worked out very, very well.
It was actually a challenge to do it with modular construction, because when you're doing that, what you'd like to do is have a continuous envelope going at all times. And with the modules, you have a module that's sealed on the one side, and the other side is indoor living space, which is sealed in its own way, but not with the same exterior insulation and moisture barrier. And then it sits next to another one, and that has its own seal. So then you have a gap there, which during the erection of the building, you have to make sure that all these gaps are sealed. And that was another closed cell spray foam that we filled in the gaps and then bridged that. So we're building them in a factory in Pennsylvania. And they have their tape measures, we have tape measures, and they should all be the same. But you kind of think to yourself, all right, well, is this guy going to make it exactly what it's supposed to be, and is it going to fit on the foundation that we gave him here? Is it going to be exact, and is it going to be inexact? So in my mind, I'm thinking to myself, like, all right, we have some tolerances built in there, but at some point we're going to run into problems, and there'll probably be a lot of kind of jury rigging and making it work in the field, and there was actually very little of that. We had one situation where there was a little bit of a bust, and it was like a 1/4-inch bust, and that was all. That was my one big surprise of how well things went.
I think the largest advantage is certainly the time savings, but in our climate, it really gives you that opportunity to be dried in a lot sooner. It couldn't be more relevant than in central New York weather, and especially going into the winter. Too often, our construction cycles and the way we sequence our work is a function of our climate. This kind of allowed us to beat that issue. We spent a little bit more maybe on the construction, but when it was all wrapped up with the savings in the winter conditions and the savings in the time, it all squared out.
I just like how each floor has like a sitting area and you can just hang out, and I got really lucky. Most people don't get it this nice in their dorms.
As mentioned, the $31 million residence hall did achieve gold certification from the U.S. Green Building Council's Leadership in Energy and Environmental Design program. And one of the reasons for that achievement was the site preparation, starting with the removal of the old houses that used to line this street, using a combination of deconstruction and demolition. Here's what the traditional demolition process looks like. Heavy equipment brings down the house. Then the pile of rubble is carried off to be buried in landfills or burned in incinerators. Here's what the more ecologically friendly method of deconstruction looks like. Workers salvage reusable materials, like sidewalk paving stones, so organizations like Habitat for Humanity can put them back to use somewhere else.
Well, right now we're going to try to stuff it all in a warehouse because we don't have any room for it in our store, but eventually it's for sale to the public. And we donate a reasonable portion of it to other nonprofits when they have needs. They call up and need a furnace or a water heater. If we've got something, they can have it, or whatever. Out of this house, we've pulled, I think, 14 doors, about 300 square feet of maple hardwood flooring. We'll be taking all the porch posts and the old banister that was on it, banisters from inside, electrical fixtures that are antique and stuff like that. In this case, we didn't get one, but most of these houses have either a clawfoot or an old cast iron pedestal bathtub in them, and we pull those. I suspect out of 18 houses we'll get 6 or maybe 7 kitchens total. So
many developers and communities cling to demolition, but deconstruction is growing in popularity.
It is across the country a significant movement. There's a gentleman out in Washington State who runs his own business now. He, in the past 10 years, has taken down 2,500 buildings himself and advised on over 30,000 coming down, including complete Army bases that have been decommissioned, to individual houses, to all kinds of other structures. If you count just the dollar today, maybe as much as 10% more expensive depending on how far in you go. What the gentleman from Washington proposed here would have come out almost dollar for dollar even with what we were going to do, but we would only have salvaged about 50% of the salvageable material to meet the time frame and the budget. Really full-scale deconstruction is economically viable if you figure in the cost of carbon sequestration. All the material that is being knocked down and hauled away here is either going to rot and release carbon, or it's going to be burned in the incinerator and release the carbon back into the atmosphere. So environmentally, there's a very strong argument for doing this.
And Greg Wright with Habitat for Humanity says the salvaged building materials and appliances are cleaned up and inspected before being put out for sale.
We are very selective. I don't want junk out there because probably almost half of our business is with local landlords, and if we're going to change the quality of life for people, the landlords have to be able to afford to make the places better and more energy efficient. We handle only energy efficient windows, energy efficient appliances used. We don't handle the older stuff because it's just too expensive for people to use.
If you're interested in the program, visit syracusehabitat.org.
Look at areas that have more light than we need, take out some light bulbs, de-lamp, if you will.
De-lamping might be one term for it, because one of the suggestions or the outcomes may be reducing the number of lights.
I didn't want the library turned into the inside of a dog. If you know the Groucho Marx quote, you know, outside of a dog, a book is man's best friend. Inside of a dog, it's too dark to read.
Some students came to us and were interested in reducing the lighting levels in the library, which might be the last place you would think of.
And what I noticed this morning at about 10 o'clock or 10:30 was this side of the library that has been delamped had about twice as many people sitting here as the side that hadn't been.
We speak there unveiling the modern sculpture, one of the most popular exhibits here.
Normally a sculpture like this would be thrown away and it goes to waste, when we can use it to make 100 gallons of usable diesel fuel.
So we're going to separate out the proteins, the sugars,
and the water away from the fats, and we're going to take those fats and we're actually going to use the fats with our bioprocessor that we have on campus and convert that into biodiesel itself.
The mileage is nearly the same as petroleum diesel. It's a little bit less, but the equivalent of octane is a little bit higher, so you get better wear on your motor.
It's easy to just throw stuff in the garbage and forget about it, or flick on a light switch and not think about where that energy is coming from, but everything we do has an environmental impact, and students can come here, participate firsthand, learn how it works, and take that knowledge back to wherever they're from and maybe do a system like this in their own community.
This parking lot may look like any other parking lot, but it's really quite different, with a lot of green infrastructure built in to make it environmentally friendly. Specifically, it's designed to help manage stormwater runoff. Landscape architect Tim Tolan gives us the tour of the finished product.
I'm standing in the middle of a rain garden that's been installed in a new parking lot project that we have here on campus, and there's several stormwater management facilities and structures that have been put in place here. Most significantly is this rain garden that extends all the way from the upper end here down to this lower basin here. And the way this is designed is it's meant to take all the surface runoff from the driveway and the parking areas and collect it in this basin and allow it to slowly infiltrate or filter into the ground. In addition, we've got porous paving in the parking areas that will allow some water to move through. We've added the stone riprap along the edge here to slow the velocity of water down so that we're not prone to erosion and not creating a lot of flow that's moving the mulch and eroding the soils and such. And it provides an edge between the parking area and the plantings so that if a car encroaches, we don't have to worry about damage to the plants. One of the things that's important in this climate with plant selection in rain gardens is dealing with salt. And salt is a common de-icing element, and for its cost and effectiveness is probably not going to go away. So all the plants that have been chosen here are very salt tolerant, including several species that are native to inland salt marshes in this region. So we're trying to focus on native plants. In addition, all the plants here are herbaceous so that we can pile snow. When they plow, they'll just pile this area up. It'll be a snow storage area so that we don't have to truck it, haul it off to other parts of the campus. In addition, what you don't see is below are several subterranean storage tanks, and those are designed to accommodate really heavy flows, and they take water directly off of the roofs, and they hold water for a period of time so that we're not releasing all of the water from the site into the city's stormwater sewer system. That's really to help prevent combined sewer overflows, which is when we have too much water coming into the system, combining with the sewage, which creates direct dumping into the Onondaga Creek and Onondaga Lake. In addition to providing water quantity control, they provide water quality control, and so brake dust, lead, other pollutants that are drop off of cars and other vehicles that get washed into them, they're held in the soil, and by the time the water percolates down through, it has been cleaned and it increases the water quality. Underneath here, there's subdrains which will carry water, excess water into the storm system, but that's essentially clean water. Well, one of the things that we had on the existing site was that we had several different alternatives for how to treat that hillside. When we built the parking lot, we encroached upon the existing hillside, and we could have built a very large retaining wall as a singular wall, and that would have been very expensive. But what the terracing also allows us to do is manage some of that water in the terraces, so it'll flow down. It will help irrigate the plants, and you can see in the middle level and in the lower level we have several plants that will benefit from that slow water movement. Many of the plants, though not quite all of them, are exactly that. New York natives, which are adapted to the climate, adapted to the snow, the rain, the cold, and those other things, which should hopefully alleviate long-term maintenance. One of the other things about the plantings here, this is a parking lot, and this is a highly visible part of our campus, and so a lot of the plantings that you see, particularly on the ends outside of the rain garden itself, were intentionally designed to help screen the vehicles from the roadway, from the sidewalks, things like that. And part of the intention with this project was that this rain garden has a functional component in that it is treating water for both quantity and quality, but the whole site is being designed from an aesthetic standpoint to better improve the aesthetics of the campus. We're starting to see a lot more of this type of construction in several contexts. It originated in the southeast of the United States where the climate is a little bit milder.
Now, let's back up a bit and check out how it was done.
There's several things that fall under the general category of green infrastructure as part of this project. We're putting in a rain garden as part of the stormwater management strategy. We're putting in storage tanks underground that will hold water to minimize the impact of our stormwater runoff off the roofs of the buildings and off of the parking lot to help the city with its combined sewer overflow issue. We're putting porous paving in the parking aisles so that water will infiltrate. And we're going to increase the amount of planting, various plants, both natives and ecologically friendly exotics, for both increased canopy coverage to mitigate the heat island effect with paving, but also to help with our teaching needs and things like that, so that we can have a greener campus. There's certainly an increased upfront construction cost associated with certainly the storage tanks because of the depth of excavation on this project and the number of tanks that were used. There's more material, there's more excavation, there's more labor. So there is a cost there. The rain gardens too add somewhat to the initial upfront cost, but what we're looking for are long-term savings that are associated with each of these infrastructure types of green infrastructure. So hopefully we'll have less wear and tear on what surfaces we do have, on what materials we do have, that the plants and the infiltration can mitigate the need to replace the municipal stormwater sewer system, which is right now near or over capacity, and help address some of these combined sewer overflow issues at the larger scale. So you have to balance the cost issues when you're talking about green infrastructure. Yes, there's some additional costs directly related to them, but there's other costs associated with the maintenance and management that are reduced because of them. The combined sewer overflow is one of the things that a lot of cities do. It's not just Syracuse, a lot of cities across the country, in particular in the Northeast. At the time it was a good idea, rather than having multiple pipes in the roadway, let's just combine them all into one. But as development has occurred over the last several decades, we have more impervious surfaces, faster runoff rates, and the systems just aren't generally designed to accommodate these higher flows. The city has mandated some of its stormwater management policies to require people to start managing them on site, because if you look at the cost to the city and to the state, it's exorbitant. There's going to be a green space. The parking is going to be on this side, and so there's going to be two bays of parking with a drive aisle coming through it. There'll be a roadway on the Bray side of the Robin Hood Oak, and so that road's going to connect up to the existing intersection. And so the rain garden's going to separate the drive aisle from this parking over here, and again have a lot of plants in it. We're going to use many plants that are salt tolerant. One of the things with green infrastructure, rain gardens, and other bioretention strategies in this climate, because of the prolific amount of salt that's used on the roads, you get a lot of salt-laden runoff, and most plants can't tolerate it. But interestingly enough, in the Syracuse area, there's a native plant community, the salt marsh community, which is highly tolerant of a high concentration of salt, and is a native plant community that we can plant and promote as a way of kind of mitigating the problems associated with salt. It's a very dynamic landscape. Our summers are quite beautiful. We have really harsh winters, and some winters are worse than others. Some summers are rainier than others, and so we have a lot of variability just kind of because of the unique location that we're in. As we start to understand the systems and we start to better understand the plantings, we're starting to see it adopted more and more across the country. Both from a regulatory standpoint, a lot of jurisdictions are very concerned about stormwater management, about water quality, and have combined sewer overflow issues. So these kind of structures are kind of finding a lot of niches in a lot of development, mainly because you can do a lot of good in a very small area. Whereas traditional gray infrastructure requires a kind of a centralized approach and big infrastructure gestures. This green infrastructure element can be tucked and fit into parking lot islands, kind of the leftover residual spaces along the edges of parcels, along planting strips, along roadways, and so we're starting to see it used more and more. In the end, I think this will be a good demonstration piece for how this can be, how this technology, how this idea can be fit into a site, both in an aesthetically pleasing way, but also to achieve these very important functional goals.
Depending on what you're looking at, basically both of them are environmentally harmful and neither of them are necessary. We've listed a number of different kind of characteristics, ways of measuring the difference between paper and plastic use in terms of impact on the environment. If you look at the amount of energy in consumption, plastic tends to be better, it uses less energy. If you look at the amount of energy used in transport, plastic tends to be better. The amount of space in a landfill that's used up, again, plastic tends to be better. The amount of water used, plastic tends to be better. If you look at litter and how long it stays around, you see plastic bags everywhere. Clearly, paper is a better option. If you're looking to the threat to marine life, paper is better. Plastic bags tend to clog drains, which becomes a problem in terms of the toxic chemicals in the bag itself, not necessarily in the production of it. They're about equal because of the way that the paper bag is produced. And in terms of recyclability, neither of them are terrible, easily to recycle. You don't need to buy a special bag that somebody produced and is selling. They're good, they're better, the fact that you can keep using them. But, I just tend to bring a couple of plastic bags with me and just reuse them.
One final piece of construction to look at, the Gateway building, under construction now and scheduled to open in the summer of 2012. When it does, it will showcase some of the latest developments in environmental construction and technologies. The design includes a high-performance building envelope with a bioclimatic facade that controls thermal loss and solar gain to minimize building design loads, use of renewable fuels to help lower the college's carbon footprint, installation of a photovoltaic system, and a garden roof. The Gateway building includes the construction of a new combined heat and power system that provides steam and electricity to the Gateway building and 4 additional campus buildings. While 4 turbines generate electricity, the resulting heat will be recovered from both the steam boiler and turbine exhaust for distribution to the campus and for use via heat exchangers in the Gateway building itself. Cooling will be provided by the existing high-performance chiller plant in ESF's Yon laboratory. Overall, it's twice as efficient as traditional technology. Other environmental aspects include the sustainable green roof, which will be made with plantings native to central New York, and be part of a walkout observatory deck offering a panoramic view of the hills and valleys to the west of Syracuse. Rain gardens will be used to control stormwater runoff, and as you can see, a significant amount of natural wood and recycled materials have been incorporated into the project. That's it for this edition of Improve Your World with SUNY-ESF. Thank you for watching. We hope you'll tune in again next time.